As humanity advances towards delivering people to Mars, information about the planet continues to be demanded. Current designs for Mars exploration aircraft have been extremely limited by propulsion systems, which come with large penalties due to weight and limited fuel availability. This results in decreased mission time and thus less information gathered. However, what if the propulsion system was removed entirely? Here on Earth, gliders can achieve extremely long flight times by effectively using atmospheric energy. The inspiration for this type of flight comes from the albatross, a bird that can glide for thousands of miles over bodies of water with minimal expenditure of energy. This method of flight, called dynamic soaring, can extend flight times indefinitely if used correctly. Harvesting naturally occurring energy in the atmosphere, such as wind shear layers, thermal pockets, and air rising over geological features, provides the necessary lift and speed gains to counteract energy loss from drag. The question then stands, with an atmospheric density only 1/100th of that on Earth, can this type of flight take place on Mars? In order to answer this question, the Mars Albatross project aims to send a glider to Earth's upper atmosphere, where density is comparable to that of Mars. We have designed systems to lift it to high altitudes, release it on command, and track its telemetry in real time as dynamic soaring loops are attempted.
The Albatross 1 is a 2.9-meter wingspan glider designed for testing the efficacy of dynamic soaring in low-density conditions. The high aspect wings provide a large lift-to-drag ratio, allowing for efficient flight with low energy loss. Advanced soaring maneuvers are made possible through its control surfaces, which include rudder, elevator, and ailerons. To make landing easier and safer, it can also make use of spoilers present on the wing. A single brushless motor on the front of the glider serves two main functions. It is primarily used to generate electricity to extend the life of the onboard 2-cell lithium polymer battery. Once the mission is complete, it will also allow the Albatross to return to its launch site against the wind. Powering the Albatross 1 is a Pix-32 autopilot system, allowing for precise maneuvering at large distances. The Pix-32 is paired with gyros, accelerometers, a barometer, pitot tube, GPS, and compass. These sensors provide accurate real-time tracking of glider position and orientation throughout the entirety of its flight. The Pix-32 runs on ArduPilot firmware, allowing for the creation of pre-planned flight missions using waypoint navigation. This helps reduce input delay and creates a smoother flight, keeping energy loss to a minimum. Auxiliary to the Pix-32, an Arduino Nano controls various emergency mitigation systems throughout the plane. This includes the release of an emergency parachute or automatic detachment from its lifting device should the communication system find a fault. The onboard high-powered DragonLink and video transmitters enable consistent communication with the plane over a range of 100 kilometers. This, however, is only achievable with the included directional tracking antennas. Featuring an easily produced, lightweight, low-cost 3D printed housing, two high-precision high-torque servo motors, and an embedded Linux computer, this antenna system supports advanced tracking functionality on a modular, adaptable base. It is compatible with any directional antenna up to 3 kilograms with proper counterweighting. As the connected DragonLink receives GPS position data from the Albatross 1, the onboard computer uses advanced tracking algorithms developed in Python to aim the attached antenna towards it. These tracking algorithms depend on the traditional bearing formula to determine horizontal angles, but a new algorithm and accompanying set of equations have been developed to find the vertical bearing angle from any GPS altitude coordinate to another. This angle accounts for Earth curvature, allowing for accurate pointing even over great distances. In addition to correctly pointing the antenna, the tracking system also creates a local area network as a bridge to pass flight data between the DragonLink and other connected systems. Furthermore, the tracking software is network-enabled, and any number of trackers can be used for the same mission. This supports the possibility of using multiple long-range antennas for video, telemetry, and any other source of data that could support a successful mission. Connected to the antenna network, 3 independent computers operate as mission control for the Albatross 1. The first initiates and monitors the tracking antenna software. This is done by pasting commands through a secure shell, though software is being developed in the Kotlin programming language to completely automate this process. The second computer communicates directly with the Albatross 1 via Mission Planner. This open-source software interprets MAVLink data and also allows the adjustment of waypoint navigation for the plane, all while displaying real-time data from its sensors. The final computer is used to track wind as the sailplane ascends to testing altitude. Using data sent down to the ground station including altitude, speed, airspeed, and more, this system calculates total energy available as a function of altitude. It then finds the most promising area to perform tests.
Setup for the mission is a three-stage process. First, the ground station itself is prepared by putting up tables, initiating laptop programs, and starting the tracking antennas for telemetry and video data. While the antennas are being calibrated, Albatross 1 is assembled and tested to ensure proper functionality. Finally, a high-altitude weather balloon is tied to the glider and filled with 220 cubic feet of helium. When everything is set, the balloon is released and rises at a nearly constant rate of 5.9 meters per second. While it moves, the tracking antennas point toward the glider and follow it on its journey. During the ascent, wind data is constantly tracked by the ground station. Once the glider is near 100,000 feet or a suitable testing zone is found, the release burn commences and drops into a dive to accelerate towards cruise speed. The glider then levels out and begins attempting dynamic soaring. To achieve at this altitude, the glider will dive in and out of different wind shear layers in the atmosphere, gaining energy from faster flowing layers that can be carried into slower layers. The maneuver to achieve this can be visualized in inclined orbit. Once numerous loops are complete, the autopilot navigates the glider back down for landing at the ground station. Success will be determined by the glider's ability to gain total energy while performing the soaring maneuvers.
In regards to preliminary testing, XFLR5 and finite element analysis through SOLIDWORKS were the two main programs used to gather data before physical testing. XFLR5 was used to collect information on flight conditions, such as velocity and sink rate, while SOLIDWORKS was used to verify that the glider could handle any stresses applied to it. From there, physical testing of our glider took place and gave the team a better understanding of how well all the integrated systems work together. A few updates to our project after testing included creating tracking antennas to not lose communication, as well as retrofitting ailerons to improve the glider's stability. If high-altitude glider flight is what you need, the Albatross 1 is the bird for the job. With a balloon system that can take the glider up, a release mechanism to let her fly, and ground station tracking equipment to monitor the flight telemetry, the upper reaches of the atmosphere are not as far away as they seem. Although the high-altitude testing was unfortunately not able to take place due to our shortened timeline, the systems we have engineered will be incredibly useful for the future testing of this idea. If low-density dynamic soaring can one day be proved feasible, it would be invaluable for advancing knowledge of our neighboring planet.